I could do that, but yeah. Go ahead.
So, good afternoon, everybody. Welcome to the first philosophy colloquium of the year. Just to avoid any confusions, I am not Jack Zucco, but I am going to do the first introduction. Before I introduce the talk, actually, I would like to just go through the logistics for today, so to speak. So, after the talk, we are going to take a short break. Then there is going to be a questions and answers period, and then we are going to go to the faculty club to imbibe on beer, and then those who would like to join Professor Dunn and myself, we are going to go to a dinner, so that's roughly the plan for today. So, as you might see, I am wearing a t-shirt for the occasion, and if you think that you are seeing red, then you are wrong. You are seeing cream and crimson, which are the colors of Indiana University, and the outline here is the outline of the state of Indiana. It says that question critically, think logically. I would like to emphasize that part, and Bloomington is somewhere here. So I'm very pleased to be able to introduce the speaker today, J. Michael Dunn, who is Professor Oscar Ewing Professor Emeritus of Philosophy at Indiana University. He's the Emeritus Dean, the founding Dean of the School of Informatics, which is nowadays also the School of Informatics, Computing Science, and Engineering. And he's also a member of the American Academy of Arts and Sciences, and he has various other distinctions that he received during his career. For example, he's also has been named the Sagamore of the Wabash, which is related to the state of Indiana, one of the highest distinctions one can receive in the state of Indiana. And he's going to talk about R-Mingle, which is actually a logic that he created. And so, please welcome Professor Dunn.
Well, it's nice to be here again. As I was telling Jack, it's kind of like coming home again with Costa and her grant. And I've been a contributing collaborator on. Anyway, it's made a good excuse for coming here and seeing all you nice people. And I might say that I told Costa the thing that's on her T-shirt is actually engraved in limestone in Indiana University. Indiana University Bloomington is surrounded by limestone, from which many of the most famous buildings in North America have been built. The Empire State Building, the National Cathedral, the Pentagon, and so on, right? And it's nice to have a piece of limestone with all those nice words on it. But right outside, the campus administration building. So, I apologize in a bit. This is a somewhat technical talk. I remember years ago walking by an office and somebody was giving a class in speech and culture, and she was saying now to the students, now if there's anything you don't understand, please ask me. If there's a sentence, a paragraph, even a single word you don't understand, please ask me, right? And I thought to myself, gee, I deal in not just paragraphs, but in whole lectures. And that's the way you come to understand things sometimes, is by getting a big wave of it, right? You get at least something that, sticks. Anyway, I'm hoping that's the case with you, and don't hesitate, though, to ask me if there's a single word. And of course, you can save it for the Q&A period if you wish. So, R-Mingle is good enough as a paraconsistent logic. Oops, I can't believe this. Oh my. I'm going to skip this slide. I thought I had it there. There is this saying, some people attribute it to Voltaire, do not let the perfect be the enemy of the good, right? It's been attributed to a lot of people, including a former teacher of mine, Wilfred Sellers. You can Google and find him being credited with that. And that's kind of what this talk is about. That, you think of logic, I certainly was drawn to logic because of certain considerations about its being perfect, right? Gee, there's probably no such thing. And this talk is based in some indirect way, at least, on something I've been working on recently. I even gave a talk here on this about a year ago or so, about logics as tools, right? Mm-hmm. Logics are, in a way, human inventions created by humans for certain purposes, having to do with deducing information, whatever that means, from other information. And there's probably no one such thing as the perfect tool. And one of the things I want to do is tell you about this logic R-Mingle, which I think has been overly neglected, and say something about why I think it is good enough for certain purposes. Now, paraconsistent logic. What is a paraconsistent logic? Well, all of you have taken a course in logic, or especially taught a course in logic, know about the embarrassment of showing students that P and not P implies Q, right? That no matter what P is, P can be snow is white, and Q can be moon is in the heaven, and P and not P will entail Q. And that's not a paraconsistent logic. That's the ordinary classical logic, or even modal logics, right, that we're used to. From a contradiction, you can entail everything. Now, that is, of course, for many purposes, maybe not such a bad thing. But for certain purposes, it might be a very bad thing. For example, and we do this more and more, I'm afraid, delegate our reasoning to our information assistants, right? Mm-hmm. Otherwise known as computers. Right. And we do not want to have a system whereby a very small contradiction will lead to some totally different and very bad thing, right? Many of you use the internet, I'm sure, the World Wide Web. I'm sure many of you have used it for trying to find out how to fix things. Mm-hmm. Could be fixing a computer, could be fixing your car, could be fixing a disease. You're about ready to see a doctor, you've seen a doctor, etc., right? You would not want to use a search engine that basically said, wait a minute, if I find any little inconsistency here, I'm going to just tell you you're going to die. Right? I mean, you don't want something like that. You want something that will tolerate inconsistencies. And the World Wide Web is really based in many ways upon inconsistencies. And we all know you can find almost anything you want on the World Wide Web. And many things you don't want. And especially in this information age where we have people, taking over certain websites and publishing information, quote unquote, on Facebook or Twitter or so on, right? Mm-hmm. And so I think the idea of a paraconsistent logic, a logic that can go on even with minor inconsistencies, is a very good idea. And there are a number of those that have been developed. And Newton de Costa in Brazil started all this in some ways, and in the 50s, I think it was, 60s, sorry, with the idea of paraconsistent logic, and Graham Priest has become very famous for not just paraconsistent logic, but what he calls dialethic logic, where contradictions aren't just to be tolerated, in some instances they're to be praised, right? Like the Russell set's a member of itself and not a member of itself. Yeah! But from that, you don't want to go on to conclude, that arithmetic is inconsistent or something like that. So anyway, I want to talk about R-Mingle as a good enough paraconsistent logic. Now, I've been involved most of my career with so-called relevance logics. I was a student of Belknap's and Anderson's, and at Pittsburgh, University of Pittsburgh, in the 60s, and I they're the ones, now there's a long history here, you can go back to Church and Moshakwe and to a whole bunch of earlier people who worked on these things. Orlov, and in the 20s, I guess, who worked on relevance logics. But Anderson Belknap were the first ones to, I don't know how to put it nicely, maybe industrialize Pittsburgh is the right idea.
That's good.
But they put things into real packages, right? It wasn't just isolated works. And you probably, some of you have seen anyway, there's Anderson Belknap, Entailment, Volume 1, and Entailment, the Logic of Relevance and Necessity. And that's all about their system E of entailment, but also about the system R of relevant implication. And as I'll say in a little bit, E could be thought of as both a relevance logic, like the system R of relevant implication, and also a modal logic, like say the system S4. So you can think that A entails B means something like A relevantly implies B. And, oh yeah, and furthermore, it's necessary that it does. So when they worked on these systems, they created the Entailment Volume 1, about that thick, I think. Then Entailment Volume 2, I was a co-author on that one. I was a contributing author on the first, about that thick, right? And they made, I don't know how to put it, but this relevance logic a serious business. Now, relevance logics rule out P and not P arrow Q. Not because they don't want contradictions to imply everything. That's a kind of indirect benefit. What they didn't want was one sentence to imply another sentence when it's not relevant to it. So if P and Q are totally different things. Snow is white and the moon is in its heaven. You don't want the one thing to imply something that's irrelevant to it, right? If we teach informal logic, we even talk about fallacies of relevance and so on. So the idea was to somehow codify that, symbolize it, formalize it. Now, the thing that RMingle is not, it's not a relevance logic. It's almost a relevance logic. And I think I'll just use that as the introduction to my talk and go on from there. So, how did this system R-Mingle start? There was Shion Matsumoto in the early 60s produced a system where they were trying to avoid certain paradoxes of implication, and they had a so-called Mingle rule. I'm not going to dwell on that, but I was trying as a graduate student in Storr McCullough's class. Storrs, as you know, has been a professor at McGill for many, many years, and I think still is. And he, there had been a certain problem, and the problem was to show that the system E of entailment was the intersection of two other systems, the system R of relevant implication and the system S4 of modal logic. And it turned out that that wasn't so. Saul Kripke gave a counterexample. And various people tried to show that E was, the entailment system was the intersection of R with other systems. And Storrs suggested to me that I should look at this system gotten by adding the Mingle axiom to E Mingle. And that came out of Onishi and Matsumoto. And that led to a whole lot of work on the R-Mingle, including a work I showed in the 1970s that every normal extension of the logic, so-called R-Mingle, has a finite characteristic matrix. This is similar to something Joe Scroggs had showed in 1951 when he showed the modal logic S5 to have this property. Now, curiously enough, I never pursued that question in my term paper about whether E was the intersection of R and E mingle. I got involved with a so-called Gensen system for the implicational fragment for Storis McCall's class back in 1963, my first year, second semester at Pitt. And I'm sorry to say, though, after all these years, the problem of whether E is actually the intersection of R and E mingle still remains open. So there's something for all the students here to show. I mean, that's, 50 years and more, so curious. Now, I'm going to be defending R-Mingle here, and I'm not the first one to defend the niceness of it. Robert K. Meyer, Bob Meyer, first proved R-Mingle complete with respect to something called Sugihara matrices. I'll explain these later. And says in one of his contributions to Anderson Belknap, that's Entailment, Volume 1, I like Mingle, as a reader will discover, for two reasons. There is a tension between them. First, its theory of deduction, due to Dunn and McCall, both in motivation and formulation, simplifies the Church theory in a reasonable way. Church had this weak calculus of implication, which was turned out to be the implicational fragment of the relevance logic R. Secondly, it's useful for many of the things that R might be good for, while being much more easily visualized. On the other hand, this involves the breakdown of the relevance principle, undermining the raison d'etre of the enterprise. Then he goes on to say, as I argued, sometimes one doesn't need the whole relevance principle. And on these occasions, R-Mingle is good enough when some relevance is desirable. Indeed, this is proven very useful by illuminating, in a context that is technically simple, some of the relevance features shared among RM, R, and E. R is the relevance implication system, E is the entailment system. Nevertheless, one must confess that the whole system happened by accident. Nobody thought that a mild modification of R would produce a system this strong. He's entirely right. As we'll see, R-Mingle, if you think of it naively, as I certainly did, when you first see it, looks like it should be almost the same as R. Just a little different. But it turns out it's very different. What Meyer's referring to is that the simple addition of the seemingly relevant implication, you see it, A implies that A implies A? That is the so-called mingle axiom. You might not see a mingle in there, but it's because mingle can be viewed as a rule. That is, if you have A implies B, and you have, A implies C, let's say, and you have B implies C, then you have that A implies that B implies C. Well, if you have A implies A and you have A implies A, you get A implies that A implies A. And it turns out that actually gives the whole mingle rule if you work on it. And it leads to irrelevant implications such as, look at that one, A and not A implies B or not B. I gave that the name safety. Why did I call it safety? Well, I think it had to do with trying to prevent terrible accidents from happening. If you have A and not A entails B, and you think of logic as somehow built in this computer, right, regulating, say, this power system, a tiny little glitch, right, could lead to the shutdown of the entire power system, or perhaps turning up the power so much that all the switches melt or something. So you want to don't want that to happen. But here what happens is, if somehow there would be a small glitch, instead of turning all the switches off, as it were, it just leaves them on if they were on already. B or not B. If it was already there, yeah, it's still there. It's not like we get just everything melting down. We just get the things that were on already to stay on. That's it. Nothing. So RM, like R and E, does not satisfy the Anderson-Belknap variable sharing property. The variable sharing property there is A arrow B is a theorem only if A and B share a sentential variable. The system R of relevant implication and the system E of entailment both can be shown to have that property. So you never have anything like A and not P and not P implies Q or not Q. It just wouldn't happen. But here you have it. But what you don't have is the much more dangerous P and not P implies Q. Meyer showed it satisfies, R-Mingle satisfies a weaker version with an escape clause. The weak variable sharing property is A arrow B is a theorem of R-Mingle only if either one, A and B, shares an intentional variable. That's just like the system E and R. Or, and this is R-Mingle, not A and B are theorems of Rm. So it turns out if A implies B, then either A and B share a propositional variable, or something extreme happens. A is false and B is true. In which case, no harm. B is true. Who cares? If you infer it. So that's the motivation. The escape clause not only allows the breaking of the variable sharing property, as Meyer showed it allows the breaking of the variable sharing property, as Meyer showed, it requires it. Let's suppose not A and B are any two theorems of R-Mingle that do not share intentional variables. Then you can prove in Rm that A implies B. There's the proof. And these proofs are somewhat informal. I mean, you know, if it was an introductory logic class, we might be a little more explicit. But I think you'll get the idea. So suppose we have not A is a theorem and B is a theorem. Well then, of course, line 1, you can get not A and B by the rule of adjunction. You just form their conjunction. Then you've got this funny formula, C implies that not C implies C. That's a little strange, but we have not C implies that not C implies not C. That comes from Mingle. It's a special case. Put not C in for the formula. And then you can use contraposition to turn the not C arrow not C around to C arrow C. And now we've got not C implies that C implies C. Then you can use permutation to bring the C outside. Now we have that C implies that not C implies not C. Then you can use double negation. Anyway, we've got not C implies that not C implies not C. We get not C. I can't do it. Can I use the board?
Yeah, go for it.
Sorry, I was going to
Yeah,
suggest.
there's chalk right here.
Away. Thanks, Jim. So we get not C implies that not C implies not C. And then we use contraposition. Get not C implies that C implies C. Then we get permutation. We get the C out to the front implies not C. Sorry, C implies C. And then simple. C implies that not C implies C. That's what we want. And so we start with not C implies not C implies not C. Not C implies that C implies C. Then we get the, then permutation. So we start with this. This is Mingle with not C implied not C implies not C. From that we can then get this using contraposition and double negation, and then we can get this using permutation.
We don't need that.
Yeah, okay. I've got this here twice, that's my problem. So we get this using contraposition and double negation, and then we just move the C out and replace it with the not C in permutation, and we get this. So that is a kind of a funny little theorem, but it says that if something's true, then its negation implies it. The other way around is not so odd. If its negation implies it, right, it should be true. But that everything that's is implied by its own negation is a little bit unintuitive. So here's the interesting thing. We now put in not A and B for C. So we get this somewhat complicated formula here. Well, remember that not A and B is a theorem, so we can remove that part and we just get this part. Not the case, not A and B implies not A and B. And now we've got De Morgan's law, so we can make this to be not A or not B, i.e. A or not B. And we've got not A or not B entails not A and B. Now, since this disjunction implies not A and B, we can take the A part to be implying not A and B, and we can take the B part, sorry, the A part to be implying not A or B, sorry, I can't do this. We can get the A part to be entailing A or not B. We've got that not A and B entails B. Those are just standard things. A disjunct implies a disjunction. A conjunction implies any conjunct. And then from these two, by transitivity, we can get A implies B. So we have somewhat, how to put it, unexpected consequence that from the Mingle axiom, you can get that if A is false and B is true, that implies that A implies B. Now, these two examples are even stranger in some ways, especially the first. The first one is safety. I've already talked about that, right? That is A and not A entails B or not B, because you can prove the negation of A and not A. That makes sense. And you can prove B or not B. So the A and not A would entail B or not B. And then here's another version of it. That should be implication there. Implication negation safety, where instead of A and not A being the false thing, you take it's not the case that A implies A is the false thing and conclude the true thing, B implies B. So those are unexpected, very unexpected. Remember, you're hearing from the inventor of R-Mingle. I didn't do this. This is Bob Meyer. He saw that you could do this very strange thing from what seems fairly harmless. I mean, C implies that not C implies C, and as I said, it's not incredibly intuitive. Like, you know, this tablet is on the table implies that if it weren't on the table, then it would be on the table. That's a little weird. But it's not so utterly weird as, say, safety is, or implication negation safety. So, what is expulsum verum? It's what I just had up on the board, but I don't think I gave it the name. It's that if A is false, then if B is true, then A implies B. That's what I call expulsum falso verum. From a falsehood, the truth. Some of you may know of expulsum quod libet. From a falsehood, anything follows,
Right.
everything follows. Say from a contradiction, right? Everything follows. This is much milder. From a falsehood, not everything follows, but a truth follows. And we can prove it by taking the implication negation version of safety, not the case B implies that A implies A. You then permute it so that the not B implies B goes where the A was and vice versa. You then do contraposition so that the not B arrow B implies A becomes not A implies that B implies B. You now do permutation taking the not A out to the front and it's changing it for A, and then you do the permutation so as to put the B here in place of the A, and then the A goes where the B was, and so we get expulso verum. Here's something I don't like very much, is the strong chain axiom. If not the case A implies B, then B implies A, and it follows from expulso verum, because you have, let's start with not A implies that B implies that A implies B. Well, we do a contraposition, and we get that not A implies that if it's not the case that A implies B, then not B. Then we do a permutation, take the not the case A arrow B and put it out to the front, and we get not A implies not B. And then we get contraposition. Not the case A implies B implies that B implies A. Instead of not A arrow not B, we have B arrow A. So that says if you have two propositions A and B, and A doesn't imply B, then B implies A. Now, R-Mingle has that. And I guess I should say, in the spirit of transparency, I'm showing a fault.
Mm-hmm.
It's something that's not very nice at all. Classical logic has it, of course.
Mm-hmm.
But the system R of relevance logic does not. And given that if you have not C arrow D, then you have C or D, it's a well-known theorem of R and of the E, then you have the weak chain axiom, A implies B or B implies A. That's, just unintuitive. Now, various fragments of R-Mingle. What a nightmare. It turns out that R and E are very, very well behaved. I've not shown you their axioms. Oh, and I was going to say this and I didn't. This talk is based on a paper I'm doing for a volume for a philosopher, actually a computer scientist, logician at Tel Aviv, Arnon Avron, and it is based on that paper that I'm working on, and he's done a lot of work on R-Mingle, and I'm not mentioning it so much as I should here. But the various fragments of R-Mingle, as I say, what a nightmare. It begins as a pleasant dream, becomes a nightmare as the splendid bubbles of that dream begin to burst. But in the end, it's only a nightmare till we finally sort through the confusion of the dream and finally wake up. Then it's pleasant again. So we begin not with a pleasant bubble, but rather a firm mattress, foundation for our sleep, the implicational fragment, R sub arrow, the logic of the relevant implication of R. And R sub arrow can be very nicely axiomatized. It's pleasant then to think that the implicational fragment Rm X sub arrow, do you see the little subscript there, arrow? That's the implicational fragment of R-Mingle, could be axiomatized by just adding the Mingle axiom. A implies that A arrow A. In fact, it's easy to show this resulting system, Rm0 sub arrow, satisfies the variable sharing property. But what's that zero doing in the name? It's indicating this is not the true implicational fragment, R sub arrow of Rm. It's something else would still need to be added, and I'm not going to go into that. But the various fragments of the systems R and E are quite well behaved, but Rm not so much. I talked about a nightmare, right? This is a horse. Your argument is invalid. The implicational system Rm0 sub arrow can be axiomatized in several different equivalent ways. You can say A implies that A implies A. That's the Mingle axiom I was talking about. You've got expansion, that if A implies B, then A implies that A implies B. That's something that is the dual of what R and E have in R-Mingle too, for that matter, so-called contraction, right? If A implies that A implies B, then A implies B. This goes the other way, expansion. And then you've got what I call OM-Mingle, and that OM is for Onishi and Matsumoto, and because that really looks very much like their Mingle rule. If A implies C, then if B implies C, then A implies that B implies C. You can mingle the two premises, A and B, to get C. The first axiom is one I played with in my graduate term paper. Second of these corresponds to the Gensen structural rule. That's the dual of contraction, a special case of weakening. So the Gensen rule is if you have from gamma and A you get B, then from gamma and two A's you get B. And the third one corresponds to Onishi and Matsumoto's rule, mingle, as I just told you. That's why I've labeled it OM mingle. There's the Onishi and Matsumoto rule, mingle. Zane Parks, another student of Anderson Belknap, 1972, showed that the theorems of R-Mingle always take designated values in the following matrix due to Sobochinsky. And these are a little bit hard to see, I'm sure, but these are like truth tables, right? But instead of just having true and false, you've got three values instead of two. And so this is saying that if you've got 0, arrow 0, 0 implies 0, it takes the value 2. 0 implies 1 takes the value 2. 0 involves 2. 0 implies 2 takes the value 2. And that's basically to say if we define x less or equal to y, just in case x arrow y is designated, we get a chain. And this is basically saying 0's at the bottom, right? Since 0 implies everything. You could put it at the top. I mean, you know, it depends on which hemisphere you're in, I guess. But I think up north we definitely put it at the bottom. And I think Australians and New Zealanders do too. And 2, on the other hand, you've got 2 at the top, because 2 doesn't imply 0. 2 doesn't imply 1, but 2 does imply 2. What do I mean here? I've got a star here. That's to say the 1 and the 2 are designated. It's like they are true true values. So that's why when we put a 2 there in the top row, it's like saying, yeah, 0 implies 0, 0 implies 1, 0 implies 2. This is like saying, no, 2 doesn't imply 0, 2 doesn't imply 1, but yeah, 2 implies 2. And then 1 is somewhere in between. And negation just flips the values. 2 becomes 0, 0 becomes 2, 1 stays the same. A fixed point, as it were. Conjunction, well, I won't go through it, but has this table here, and disjunction has that table there. I mean, I'll just say a little bit of it, I guess. If you have 0, since 0's at the bottom, it's like I'm very false, right? So if you conjoin 0 with anything else, you get something very false. 2 is sort of like I'm very true, so you conjoin 2 with anything, and it becomes as false as the thing you're conjoining it with. So 2 conjoined with 0 is 0, 2 conjoined with 1 is 1, 2 conjoined with 2 is 2. Then similar things to be said about the disjunction. And so we get this chain. Now, it turns out that this is very familiar in a certain context. There's a so-called Sugihara Matrix. And the Sugihara Matrix is any chain with a 1-1 order inverting mapping, negation as it were, of it onto itself. The designated are those elements x such that not x is less than or equal to x. The negation operation, of course, is just negation. And the other operations are defined as follows. A meet B is the minimum of A and B. So it's like, you know, when you form a conjunction, it's as true as its worst element. A or B is the maximum of A and B, so when you form a disjunction, it's as true as its best element, as it were. And then this is the interesting thing. A arrow B is not A or B. That's, of course, material implication, right? The usual implication, classical logic. If A is less or equal to B, then otherwise it's not A and B. An important example is the set of integers Z with the non-negative integers designated. So 0, 1, 2, 3, etc., all designated. -1, -2, -3, etc., all undesignated. And there's a natural sequence of finite examples. little bit hard to read, I'm afraid. But there's S1, that's just +1 and -1. That's like the usual two truth values. Then you get S1 sub 1 plus 0. That's where you have +1 and -1, but you also have 0. You've got this fixed point. And then you've got S2 where you've got +2, +1, -1, -2. Then you go on to have S2 plus 0 where you've got the same +2, +1, -1, -2, but you also have the fixed point 0, etc. Sugihara matrices were introduced by Sugihara in 1955, who was looking at some issues involving logics, multi-valued logics. And Meyer, this is the Bob Meyer, showed that RMingle is sound and complete with respect to the class of Sugihara matrices. Now, Park's matrix, it turns out, and he didn't know this, I think, at the time, is actually isomorphic to the Sugihara matrix with 3 elements. You can let me go back. +1 for 2, 0 for the 1, and -1 for the 0. And if you were to rewrite those matrices, you would get exactly the same as for the Sugihara matrix. So, by arguments using matrices, one can show that one can add negation to RM0, and one can add conjunction, disjunction to RM0, and that all of these systems satisfy the variable sharing property. So if we were just looking at implication or implication negation or implication with conjunction and disjunction, they all behave very nicely. They satisfy the variable sharing property, just like R and E do. But when you add them all together, as you saw, we get safety. Conjunction doesn't mix very well with negation when you allow that De Morgan property to take place. So we have only the weak variable sharing property for all of RM, even though for these things that we were looking at, the RM0, the RM0 sub arrow, the RM0 negation, even you can have the RM0 with arrow and negation, all of them satisfy the variable sharing, but as soon as you throw them, and with conjunction and disjunction, if it's just RM with 0 with conjunction and disjunction, they satisfy the variable sharing. It's when you allow them to mix together, especially the negation and the conjunction, right, that things go, if I can put it this way, a bit sour. So, it turns out I'm not going to go into this. It gets very much like what's sometimes called Polish logic, not to insult any Poles present, but very technical, very detailed examination of what axioms you can add to these fragments to get the full fragments of R-Mingle. I mean, there is a fragment of R-Mingle with that's the pure implicational fragment of R-Mingle, and you have to add a certain axiom, right, to RM sub arrow, RM0 sub arrow, the implicational fragment that I gave you. It's not the implicational fragment. You have to add another axiom, and that can all be done, but it gets rather unintuitive. That's why I say it's a nightmare. But when you get to the full R-Mingle, everything's kind of beautiful. And let me sit for a moment and I'll tell you some of those things. Let me see. Here's my consumer report style checklist. And it's, imagine that you're buying a logic, right? You're going down to the nearest Home Depot or something to buy the logic, and you've got certain features that you have in mind as to what would be desirable, what wouldn't be desirable. And here's my consumer guide report, as it were, the summary. And first thing you probably would want your logic to be is decidable. Now, you can't always get what you want, as that famous Rolling Stones song goes. First order logic, classical logic, right, with quantifiers. I've been talking only about sentential logics or propositional logics, as they're called sometimes. But if we add quantifiers for all x, there is an x, etc., that system's undecidable, right? So you can't always get what you want, but when you're dealing just with the basics, the propositional logic, right, you think decidability would be a virtue. And if you look at it, we've got R-Mingle, it's decidable. Why? Well, you can show that something is a theorem of R-Mingle if and only if it's valid in all those finite Sugihara matrices. And so there is a decidability procedure. You can even show that if the sentence has n variables in it, then all you need to check is the Sugihara matrix Sn plus 0, and that will do. Of course, classical logic, I'm talking about two-valued logic, so I put TV, I guess I was thinking of Consumer Reports a bit too, is a decidable system. But R, this is well known to some circles, is undecidable. Alistair Urquhart at Toronto showed that the system R and the system E and a bunch of other systems of relevance logic are undecidable. He showed that back in the middle 80s. So R is not terribly desirable from that point of view. Low complexity. Well, what is complexity theory? I can't get into all that, but it basically says, look, even if something is decidable, even if there's a computational algorithm for it, there are different degrees of complexity. Some are easy algorithms, others are very hard algorithms. They take a long time, they take up a lot of space in your computer. The computer might have to run for days, or maybe you have to double its memory, or actually much more than that. Make it many, many times larger, and so on. And it turns out that R-Mingle and the two-valued logic, in fact, have the same complexity. It's something called co-NP complete, both of them. So, from a real practical point of view, two-valued logic would be a little easier because it's only got two values. But an R-Mingle has, as I said, for an n-variable formula, you'd have to looking at, actually, because you go from +1 to n, and then you'd also go down -1 to -n, you'd be looking 2n, and then maybe the 0, so you'd be looking at 2n plus 1 values. That's many more than 2 normally. And so, but still, it turns out that they have the same technical complexity. R doesn't have low complexity, but that's because it doesn't have complexity at all. There's no algorithm for deciding it, right? It's undecidable. So that's why I have NA, and not applicable. It's not like it gets a check or it gets an X, but it certainly doesn't get any good points for that. Simple, easy to interpret semantics. Obviously, TV, two-valued logic gets that. It's not obvious, maybe yet, that RM should get that. And I've not talked about this, but I'll mention it briefly. There are these matrices for RM, the Sugihara matrices. Those can be given a kind of intuitive interpretation, right? As you've got your +1, +2, etc. Things are getting truer and truer. You've got your -1, -2, etc. Things are getting falser and falser. You've got your 0. Things are both same degree of truth and falsity, whatever that means. But it turns out that I was able to give a so-called Kripke-style semantics for R-Mingle. Many of you know, I'm sure, the Kripke-style semantics for modal logics, where you've got a set of possible worlds, you have an accessibility relation that says one world is possible relative to another. You define necessary A to be true at a given world if A is true at all the worlds that are possible relative to it, that are accessible from the given world, and possibilities similarly. I was able to give a similar Kripke-style semantics for R-Mingle, but it was more like the Kripke-style semantics he gave for the intuitionistic logic. I won't go into that now, but it is definitely a Kripke-style semantics, and it has a lot of intuitive flavor to it. So I gave it a check anyway. Now, as I said at the beginning, remember my bias here. I was the creator of RM, so I may be a little generous in my grading here, but I give it a check. Constant domain semantics for quantifiers. This I'm not going to go into either, but if you think about the Kripke-style semantics for modal logics, first order modal logic, right? There are lots of issues with it. But one question is, can there be a constant domain semantics? So if I have one possible world and all these things exist in it, do all those same things exist in another possible world and another possible world, etc.? Or looking at it another way, do all the possible things, are they all in common from world to world? Not that they actually literally have to be in that world, but they in some sense have, the possibility has to be there. And it turns out that R-Mingle does have a constant domain semantics for quantifiers. R not only doesn't have a constant domain semantics for quantifiers, but it's very open as to what the any natural semantics for quantifiers is. A number of proposals have been made by Kit Fine, by Ed Mayers, and a number of people, and Rob Goldblatt. But it's very much in the air. Of course, two-valued logic, you don't even have the issue. There's just one domain for the predicate logic. So that's where those come from. The variable sharing property, well, we've talked about that. R-Mingle doesn't have it. R does have it, and two-valued logic doesn't have it. P and not P entails Q, right? It certainly doesn't have it. The weak variable sharing property, just to remind you, that says A and B either share a variable, or else you can prove A false and prove that B is true. And RM does have that, and R certainly, if it has this variable sharing property, has the weak variable sharing property, and classical logic TV simply doesn't have it. Now, in the paper I wrote about Aron Avron's contributions, I actually have not just the variable sharing property, but what he calls the strong relevance property, and then not just the weak variable sharing property, but something he calls the weak relevance property, and they work just the same way in terms of which ones have it and which ones don't. But this is easier to understand. Paraconsistency. Well, R-Mingle is paraconsistent. A and not A doesn't imply everything, though it does, remember, imply B or not B. But I indicated that was harmless, I hope. And R is certainly paraconsistent. Contradiction does not lead to any arbitrary conclusion. P and not P does not entail Q. Well, classical logic is clearly not paraconsistent. No finite characteristic matrix. Why would that be a good thing? Well, if you've got two-valued logic with just two truth values, true and false, you can prove a rather strange equivalence. You can prove that P is equivalent to Q, or P is equivalent to R, or Q is equivalent to R. Because you've only got two truth values, and if you're trying to separate P and Q and R, you can't do it. A sentence named after James Dugunji, who worked, I think, again in the 50s on some of these issues. And it turns out any finite characteristic matrix is going to satisfy a so-called Dugunji sentence, where if you take n+1 propositional variables, and then say either the first is equivalent to the second, or the first is equivalent to the third, or blah, 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 or the second's equivalent to the third, or the second's equivalent to the fourth, or blah, blah, blah. That if you've got n+1 of these, that sentence is going to be valid. So that's kind of, from a paraconsistent or relevance logic point of view, that's kind of strange to say, that you've got a bunch of equivalent sentences that don't have much to do with each other. Now, this is where honesty lets me tell you that the no chain property is also a desirable property. because it's saying, you know, if you have P and you have Q, then either P implies Q or Q implies P. And it turns out R-Mingle doesn't have the no chain property. It has the chain property instead, right? And R doesn't have the chain property. And classical logic does have the chain property. You know, if you take P and you've got Q, if you can either make P true and Q false, in which case Q implies P, right? Or they both end up with true, in which case P implies Q, or they both end up with false, in which case P implies Q, and in either of those last two cases, P implies Q or Q implies P. So there's the Consumer Report summary. Now, let's just take a quick count. How many X's does RM have? 1, 2. That's not too many. How many does R have? Well, it's got 1, 2, 3, 3. That's not so bad. It's got that NA though. That's a bad thing, but it's already covered by the bad thing of being undecidable. And what about classical logic? Well, we've got 1, 2, 3, 4, 5. The last 5 are X's, right? It flunks. Don't buy it, even if it is on sale. So, from this point of view, RM might be said to be the winner. But of course, it depends on how much you value things, which things you value, which things you don't. And, but you know, it doesn't do so badly. So with that, I will say thank you.
So let's take a short break, maybe a 7-minute break. I guess that used to be the tradition. And so then we will resume these questions and